Hello everyone. Today we are going to derive the expression for stress of a truss element. This particular YouTube channel is for people who are interested in mechanical engineering, and I have been posting videos on finite element analysis. Hopefully I'll be solving more number of problems. I will try my best to derive as many derivations as possible in order to demystify some of the subtle and critical concepts in finite element analysis. Hopefully I will also be uploading videos on strength of materials and even in engineering mechanics, hopefully in future. Okay, so without further delay, let us try to derive the expression for stress of a truss member. I have posted at least 2 videos on trusses. In case if you have not watched them, I highly recommend that you please go back and watch those videos. They may be extremely useful because in one of the videos I have introduced the concept of trusses, and in the other video I have derived the formula for stiffness matrix of a truss member. So those 2 videos may be extremely useful for you, so I highly recommend that you please go back and watch those videos. They may be prerequisites to derive the expression for the stress of a truss member. Okay, so to begin with, let me first draw a truss member. So here we go. Let me draw a straight line. So that's a truss member. So I can give nodal points here. Maybe I can call this as nodal point number 1, and this can be nodal point number 2. That's fine. And I will put a set of coordinate axes, and the angle theta is always reckoned in the anticlockwise direction. So that's our theta. Fine. Now this truss member is subjected to certain magnitude of forces, and as a result of which the nodal point 1 is getting displaced. You see, a truss is a bar basically. So in what is the direction in which the nodal point 1 is getting displaced? Well, it can always get displaced only along the length of this member, okay, because truss is a collection of bar. All right, so the displacement is q1, and the displacement of the nodal point 2, that is going to be q2. So defining the stress is very easy because stress is simply Young's modulus into strain. Maybe I can start with that definition. Stress is equal to Young's modulus into strain. And what is this Young's modulus into what is the strain? It is change in length, which is q2 minus q1 or q2 minus q1 by convention, divided by original length, which can be L. I can rewrite this expression as capital E into 1 by L into minus 1 1. I can write this in the form of a matrix as q1 q2. It's not, well, if you just do this matrix multiplication, you are going to end up with the same equation as before. That's not a surprise. All I have done is I have written q2 minus q1 as minus q1 plus q2. Then write this as in the form of a matrix, which is very simple. All you have to do is first write the coefficient of q1, which is minus 1, then write the coefficient of q2, which is 1, followed by q1 q2. So you do the matrix multiplication, you get the same step back. Fine. Now this is capital E is the stress strain relationship matrix. It's the D matrix. All right. And this is the strain displacement matrix, minus 1 by L, 1 by L, including the whole terms. For a one-dimensional element, this is the B matrix, and these are the displacement matrix. It's U matrix. All right. So we are ending up with the generic equation for stress, that is dBU. All right. This is a column matrix. In general, it's a column matrix. All right. Now, in the next step, I'm going to take from this term, it is stress is equal to capital D, which is Young's modulus, into 1 by L minus 1, 1. And the Q matrix can be written as del matrix into U matrix. This del matrix is the transformational matrix. And what is this U matrix? U matrix is U1, V1, U2, V2, which means the displacement of Q1 along the X component, that is, you resolve it, the displacement along the X direction is U1, and the displacement along the Y direction is V1, and similarly Q2, the displacement of Q2 along the X direction is U2, and the resolved component along the Y direction is V2. So U is U1, V1, U2, V2, and the del is the transformational matrix. So that's what is this transformational matrix? Well, I cannot explain what is this transformational matrix in this particular video. You have to watch the previous video, that is the derivation of stiffness matrix for a truss element, in order to understand what is this transformational matrix. So it's just I guess that video runs for around 15 to 20 minutes, I guess. So you should be able to understand what is this transformational matrix. Okay, into capital E into 1 divided by L minus 1, 1, followed by the transformational matrix, which is C S 0, 0. It's 0, 0, C S. So this is the transformational matrix, followed by the displacement matrix, which is U1, V1, U2, V2. All right. Now, all I have to do is multiply this matrix with this matrix. This is a 1 bar 2 matrix. This is a 2 bar 4 matrix. So the resulting matrix is going to be a 1 bar 4 matrix. You're going to end up with a 1 matrix and 4 column. I'm sorry, one row and 4 column. That's right. All right. So, okay. So in the next step, I'm just going to do the matrix multiplication. That's the, I guess that's the last step. So sigma is equal to capital E divided by L. The first row into first column, you're going to get minus C. The first row into second column, you're going to get minus S. All right. The first row into third column, you're going to get C. The first row into fourth column, you're going to get S. Followed by U1, V1, U2, V2. That's it, guys. So this is the formula for a stress of a truss member. It's a very simple derivation that you have to use this formula in order to compute the value of stresses. By the way, what is C and what is S? I didn't tell that. I was under the assumption that you should be knowing what is C and what is S. C stands for the cos theta and S stands for sin theta. And what is this theta? Remember, theta is always measured in the anti-clockwise direction. And you have to put the coordinate at the least node. You should not be putting your coordinate system here and measure angle. That's wrong. This is the right one. And if you're putting it here, it's wrong. Always put it at the least node. Out of 1 and 2, which one is the least one? It is 1. So suppose if you are marking the nodal points this way, 1, 2, you put the coordinates here and measure it in this direction. So that's going to be your theta. All right. So why do we do that? Because you just want to be consistent so that in your assembly, there is not going to be any mistake when you solve the problems. Thank you all for your patience. Thank you so much.